All right, so we talked about cellular respiration, and that was on the cellular level that we had all of these little processes going on in order to create ATP. But that's cellular respiration. That's different than the respiratory system and the function of the respiratory system. What does the respiratory system give to cellular respiration in order to create ATP? What do we get from the respiratory system? We get oxygen from the respiratory system, and we get rid of carbon dioxide. So that is essentially the function of the respiratory system, is the exchange of those gases so that we have the oxygen that we need and we can get rid of the carbon dioxide. So the function of the respiratory system, and then I've got respiratory system on that side, and it doesn't say function up there, but it should. Function of the respiratory system is just the exchange of gases. We need to get in oxygen, we need to get rid of carbon dioxide. Do you remember why oxygen is so important, especially in terms of cellular respiration? Say that again. Sure. What is it doing in those cells? Why is that so important to that cellular respiration process? So remember when we had the kidney bean mitochondria? Little notes, then we had all the little foldables. Okay, at least we got that part right. So oxygen didn't come into play until at the very end. At the very end in that electron transport chain. So that oxygen at the very end there, it is the final electron acceptor. And because it's the final electron acceptor, it allows all of those electrons to be moved along the electron transport chain. And when they get moved along the transport chain, they help those give the enzymes that are embedded in the membrane to give them the energy they need to pump the protons out, the hydrogen ions. So hydrogen ions form their concentration gradient, move through ATP synthase, turn it like the little paddle on a hydroelectric dam to create ATP. So if we don't have oxygen, we don't have concentration gradient, we don't have electron transport chain, we don't have ATP. So that's why oxygen is so important. CO2 is a waste product. We need to get rid of it because if it stays in our body, stays in our cells, it makes things acidic. So we don't want that to happen. What was the name of the tool that we used to measure our lung capacity? The spirometer was the tool that we used to measure our lung capacity and to evaluate the function of it. So respiratory system, some of the major organs, if you will, the major region for the respiratory system, thoracic cavity. Do you remember what the thoracic cavity is? Do you remember what thoracic indicates? Thoracic is chest. So abdominal cavity, belly, abdomen. So thoracic cavity, abdominal cavity. All right, so I had my little plastic soda bottle lungs out before. Do our lungs have any muscle tissue in them? No. We might have some with the vascular tissue like the blood vessels, because they're going to, but lungs themselves, they don't have muscle tissue. So how do they contract and expand? How do they open and close to let air in and let air out? Diaphragm is key. Diaphragm is one of the muscles that are very important. There's another set of muscles that are also very important. So within that thoracic cavity, we need to change the volume. We need to change how much room is in there. If we have more room, it's going to pull air in. If we have less room, it pushes air out. More room pulls air in. Less room pushes air out. So besides our diaphragm, we also have muscles to help increase that thoracic cavity. The ones that run along our ribs, in between our ribs. No, those guys are more along, we're moving our shoulders and stuff like that. Now, these muscles are also involved in some of that movement. But for breathing, we're talking about the intercostals. In between, intercostal muscles. Those are the rib muscles. So if you make barbecue ribs, yum. Those are intercostals. So that's changing the amount of volume that you have in your chest cavity. More volume means less pressure. So it allows air to move in. Less volume, more pressure, so it's pushing that air out. So you may want to make a note of the fact that thoracic cavity, abdominal cavity, intercostal muscles, those are terms we've seen before. I just threw them on there because I don't know if you might have them in your notes already. And if you have any of this stuff in your notes already, then we're just moving on with it. You might want to make a note. If you don't know what those things are, you might want to make a note for yourself what those are. I know what they are. So last week when you went through those activities, and I don't remember the HBS numbers that were on them, but when you went through those activities, they sent you to some different sites. They asked you to take notes on the upper respiratory tract, the lower respiratory tract, the conducting zone. So you had a little diagram that would help you go through that. I'm not going to go through that in detail. Because you've got all, and the respiratory zone, I missed that part, because you've got all that stuff. And I suggest, you don't have to, but using that diagram to help you see the difference between those different zones, those different areas. I do want to talk about, and your diagram looks a little bit different than mine because I think yours is bigger, but you have a diagram somewhere that has like a little alveoli on it, don't you? Yeah, that one right there. So it's on the bottom, what is that, right? Yeah. So I cut the rest of it off because I didn't need that. But I do want to talk a little bit about this alveoli. So these are very delicate structures that are within our lungs. This is where the air gets pulled into, and this is where the exchange of gases occurs. This, from heart to heart, is a blood vessel. Do you know what kind of blood vessel it is? Artery, vein, capillary. Why does it have to be a capillary? Yeah, it's like the bridge going to and from. And what's the structure of capillaries? It's kind of the bridge between arterioles, venules. It's kind of the bridge between them. Okay, do we remember the structure of an artery? Like how is the artery built? What's the structure of it? Do you remember why it needs a thicker wall? Yes, yes. So arteries away from the heart. So they receive all that blood from the heart. So they get that systolic pump. So they have to deal with more pressure. So that they need thicker walls, and the thicker walls come from muscle. Veins don't need those thicker walls, right? Vein back into the heart. So they're just carrying blood back in there. Do you remember the structure of a capillary? They're really thin. And they are very, very small. They are really small. But the idea is they're basically only one cell thick. So they're not big and thick like arteries, and they're not even as thick as veins. They have very thin walls because we need oxygen and carbon dioxide to be able to go through it. If it's this big, muscular, thick artery, you can't get oxygen and carbon dioxide to diffuse through there. It can't because it's too thick. So from the heart, I know this is from the heart. I know this is to the heart. I know this is from the heart because it's blue. So because this is blue, what do we know about the blood that's in it? Is deoxygenated blood really blue? Not really, but that's how we're going to label it. That's how we model it. And this is going to the heart, and it's red because it's... So this little capillary is showing how in the lungs it wraps around. It's like a little netting, if you will, that wraps around each one of those alveoli. And as it goes around it, we inhale oxygen-rich air in, and so that oxygen is able to diffuse into the blood. Carbon dioxide diffuses out of the blood. When we exhale, we get rid of that carbon dioxide. This is passive transport of oxygen and carbon dioxide. What do you remember about passive transport? Okay, yeah, it's going to move in and out. What? It is a form of diffusion. It's just called passive transport because it's happening passively. So that's when we were talking about like a little piece of paper underneath the door or something like that. Little bitty molecules that are able to squeeze through that thin cell membrane, that thin wall around the capillary. So we don't need energy. We don't need facilitated diffusion. We don't need protein channels in there. It's eking its way in and out through that membrane just by getting through the little cracks. But it is diffusion, so it is going to move along its concentration gradient. So when you inhale, there's like 28% oxygen in our atmospheric air. So there's more in the air that we breathe than that's in your blood. So it's going to move into your blood. Carbon dioxide, I think, is like 0.3%, something like that, in the air that we breathe. So there's a lot more in our blood than in the air that we breathe, so it moves into your alveoli. A couple things I want to make sure that you have. Function of your nose. What do we need our nose for? All right, so all of those annoying little nose hairs, all of that lovely little mucus, it actually has a purpose. It filters the air that you breathe, and especially that mucus is going to trap pathogens. So before they get into your body can destroy it. Oh, and warms the air, and it also moisturizes it too. So it adds a little bit of humidity to it. Warms it up and a little humidity. So it's not a big shock to your lungs having dry, cold air. Larynx, la 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 larynx. That's your voice box. Pharynx, that's that area in the back of your throat where your nasal cavity, your mouth, your windpipe, where all of that stuff comes together. But larynx, la 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 la, that's your voice box. And you have a diagram that has all of these parts of the respiratory system on there, but larynx and pharynx are often swapped around, and so that's a really good way to remember larynx. La 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 la, that's your voice. And we mentioned the diaphragm. So the diaphragm is that major muscle that helps us to breathe because our lungs don't have any muscle tissue in them. When the diaphragm contracts, it moves down in your abdominal cavity, and that allows you to inhale. When the diaphragm muscle relaxes, it moves up into your abdominal, into your thoracic cavity, and that allows you to exhale. So, cellular respiration equation, we put that in AP biology. Structure of the ATP molecule, we put that in AP biology, and that is another thing that kind of blends across both HBS and AP biology. I believe you should have this information, but let's go over it real quick. So this is where I put my little graph. And so each of these values, and you might already have these notes. I'm going to go through them pretty quickly. So if I'm going through them too quick, then all you have to do is email me, and I will send you a copy of this, or a link to where this video is at. But the TV value, TV on here, it's showing you from this point to this point. So these are our normal breaths. This is what you're inhaling and exhaling in a normal breath. So TV is from this point to this point. TV is the amount of air in each normal breath. You're inhaling and exhaling naturally. You're not trying to force anything. And like I said, I'm going through this quickly, so if you need it, then all you got to do is email me and let me know. So IRV, inspirational reserve volume, I think. The additional air that you can inhale. That was your, where you took the deepest breath that you possibly could. You are forcing more air in. You're trying to inhale as much as possible. So this isn't natural. This is a forcible part. You're forcibly inhaling. The ERV is the forcible exhale. So when you exhaled and then pushed out as much as you possibly could, that's the ERV. So on this graph, your IRV is showing that it goes from the top of your normal breath to whatever the top of this is, whatever you could additionally forcibly take in. Your ERV is showing that this is that part right here, so it's whatever you normally exhale, and then what you can forcibly exhale after that. So this deep inhale and exhale, it's not your normal breath. You were additionally trying to pull more in and additionally trying to get out as much as you possibly could. The vital capacity, IRV, TV, ERV. Reserve volume, vital capacity we do have on here. So your vital capacity is your deepest inhale to your deepest exhale. The RV on our chart, RV was given as 1.5 liters. I think it's liters on there. The RV is the additional air that's in your lungs that you really can't exhale. It stays in there and you can't force the rest of that out. That's a good thing because your respiratory reserve, that additional air, helps to keep those alveoli open. And imagine, I have an example, imagine like a balloon. When you blow up a balloon and blow up a balloon, let the air out, and then it gets kind of like sticky, right? And it sticks to itself. That makes it harder to blow it up because now you have to put in additional force to get it unstuck, and then you put the air in there. Maybe I'm the only one that's ever reused a balloon. Does that sound familiar? I'll give you a balloon so that you blow it up, blow it up, blow it up, let the air out, do it over and over again. Eventually, the rubber, it's kind of working on the consistency of the rubber, and it sticks together. It gets kind of shrivelly and sticks together. But when it sticks together, then you have to blow even harder just to get it to pop open and then fill it with air. Well, imagine that in our lungs. I mean, how many times do we take a breath, and that's inhaling, exhaling. So if they were to stick together, that would make it even harder and harder and harder and harder to breathe. There is a surfactant, there is a liquid, if you will, that also is produced by your lungs to help moisturize and keep them from sticking together, because that liquid in there kind of lubricates, if you will, so that it can't stick together. Your total lung capacity, IRV, TV, ERV, respiratory reserve, all of those things in there. Oh, minute volume. Yeah. So the minute volume that you did or that you're going to find, your minute volume is how much you breathe in a minute normally without consciously thinking about it. It's just sitting there breathing. And so a lot of times our minute volume is off a little bit because we're thinking about it, and that does change things. And your instructions told you that minute volume is your tidal volume times breaths per minute. And you have to find breaths per minute, and you use that graph in Logger Pro to find how long is one breath. Once you find out how long one breath is, then find out how many breaths per minute. Just like we did with heart rate. So when we did heart rate, we found out how long it took for one beat, and then we used that to figure out how many there would be per minute. But that's in the instructions if you need to go back for that. All right, so this stuff I do want to make sure that you have. So FEV is something that you may have heard on the patient visits, and this is giving you an idea of how much you can inhale and forcibly exhale. So FEV is forced expiratory volume. So you have your tidal volume exhale and your expiratory reserve volume. So what you normally exhale and then what you can exhale after that. So it's your total exhale, normal plus the forced. And this gives our respiratory therapists, it gives our doctors an idea if there's any kind of an obstruction and if you're having difficulty with inhaling and exhaling. So it's going to let the doctors know what's going on. Are there obstructions? Do you have a physical problem? So the FEV is a lung function test used to diagnose and to evaluate. So some of the questions that they might, be looking at evaluating is, how are your asthma medicines working? So you have an FEV before they put you on medication, and now you have an FEV after. Is your asthma medication helping you to breathe better? Is lung function deteriorating? So if you have cancer, if you have cystic fibrosis, something that's damaging the tissue of your lungs, COPD, you might be having a FEV test to see where you're at, and, how do you need to go on from here? What's the prognosis? How do we need to change your treatment? There is a scale, if you will, and the test is FEV1. So if your value is 80% or above 80%, then your breathing is normal. From 60 to 79% of predicted, there's some mild obstruction, and it could be something physical. You could have mucus in there, so a lot of times asthma is an overreaction from your immune system, and maybe it's just allergies, overreaction to allergies, and so you're producing too much. Asthma can also cause an obstruction by swelling those bronchi, and so that's an obstruction just simply because it's closing off those tubes. 40 to 59% mild, moderate obstruction, and less than 40% severe obstruction. All right, so we'll talk more about respiratory system issues next week, and then we're going to go back and review prescriptions. That shouldn't take too long since we've already done prescriptions, but we'll take a look at those. All right, take out your AP Bio comp book. Turn to cellular respiration, and we put a whole bunch of terms, and I realized that I had left one off. So if you've got room, then you can add it there. If not, you can put it on a Post-it and stick it in that same spot. But in your reading, and hopefully you're reading and taking notes, you probably read about allosteric regulation. We are so complicated. So allosteric regulation, here, I need you to listen to my melodious voice first. Okay, so we have coenzymes. So this might be an enzyme that needs a partner in order to do its job. So it might be a vitamin, mineral, something like that. It locks on to the enzyme, and then it provides the appropriate shape for the substrate to bond there. So you might need that for an enzyme to work. We need the right environmental conditions. Can't be too acidic, can't be too basic. So if I say too acidic, what pH number would be something that's really acidic? Say again. So give me a number. Sure. 1, 2. Those are low numbers on the pH scale, so they represent acidic stuff. But we don't want it to be too basic. So what might be a basic value? 8's actually pretty okay. It's not basic enough. 12 is pretty basic. 13, 14. So on our pH scale, we go from 0 to 14. 7's neutral. Anything below 7, we're getting more and more acidic. Anything above, we're getting more and more basic. So environmental conditions. Salinity can affect enzymes' action. Temperature can affect enzymes' action. So too hot, too cold. Substrate concentration. How much stuff do I have to work with? Do I have anything to break down or to bond together? If I don't have the stuff to work on, I'm not going to be working very fast or at all. Enzyme concentration can affect rate of enzyme reaction. The more enzyme we have, the more people snapping toothpicks, the faster the rate's going to go. But another thing, and inhibitors. I didn't talk about inhibitors. So competitive inhibitor is right there in the way. Non-competitive is somewhere else, but it's changing the shape of the enzyme so it can't work. So allosteric molecules, they're going to be something that's going to help put something in place to keep it activated or to keep it inhibited. So anything that's an inhibitor, it's not going to be a permanent sort of situation. So it's going to bond, but it's not going to be very lasting unless it's a chemical like our really dangerous poisons like the sarin, the cyanide, stuff like that. Those things end up being a permanent lock to it. But in our body, we hardly ever want permanent things locked in place, whether it's permanently going or permanently not going, because homeostasis. We want to be able to get it going and then stop it from going, and get it going and stop it from going. We want to be able to fluctuate between them. Sometimes, however, we need to either get it going or stop it going for longer periods of time, so enzymes get a little help from those allosteric molecules. So if it's an allosteric activator, then it's going to be another little molecule that hooks onto that enzyme that keeps everything open and ready to receive the substrate. If it's an allosteric inhibitor, it's going to be a molecule that locks onto that enzyme and keeps everything closed so the enzyme cannot work the way it's supposed to. It's not going to interact with the substrate. So allosteric regulation, this is regulating those processes. Activators will stabilize enzymes in the active form, will stabilize enzymes, that should be apostrophe S. So it keeps that active site open and allows substrate to bind there. Inhibitors do what you would expect them to do now that we know what inhibit means. It's going to stabilize an inactive form of an enzyme. So the enzyme's not going to interact with substrates. So allosteric regulation, activators stabilize enzymes' active form. It keeps the active site open. Inhibitors stabilize the inactive form. One of the things you have to be super careful about on the AP test, and maybe on HBS too, I know AP test for sure, is you need to make sure that you look at the X and Y axis, look at the labels, look at the labeling to make sure that you know what they're asking, what they're talking about. Because if they're just giving data, well, you might not have enough information to find rate unless you actually calculate rate. That'll give you at one point in time how much I have. But if it says rate on there, that's telling you at that point in time, this is how the reaction is going. So it's kind of two different things. So you have to make sure that you're looking at the X and Y axis, looking at the labels that are on there, and making sure that you know what you're talking about when they go through that. So I bring that all the way back because when you turned in the graphs for the substrate, yes, this was the toothpick ACE one. So the first graphs that you showed just showed how much volume of toothpicks, how much substrate that we processed in a certain amount of time. And so a lot of those graphs looked a little bit like this because this is what we're processing and this is what we end up with. On a graph like this, if we're talking about volume, and this is time, during here, we definitely have a reaction that's going on because we have an increase in volume. I'm kind of going back and forth between the catalase in the toothpicks graph, but let's do catalase for just a second. So if this was a catalase graph and we graphed it this way, this is showing you that more oxygen is being produced. Oxygen is being produced. I have more oxygen, so it's continuing to be produced. This, I no longer have additional oxygen that's being produced, so that means that the rate has stopped, the reaction has stopped for some reason. For the toothpick ACE graph, I think just about every time where we had the reaction stop was simply because we ran out of toothpicks. That's it. Because every other line kind of went up. But whenever that flatlined on that graph, that was because we ran out of substrate. And so we couldn't produce anything more. So if this is the oxygen production, if this is catalase, we had oxygen there, but we couldn't produce any more. We ran out of substrate to create it. But that's entirely different. If that doesn't say volume, if that says rate, and this is time, now you have an entirely different graph. Because if this is 1, 2, 3, am I still producing oxygen here? That's when I'm not producing oxygen because I have zero rate. I have zero going on. So this is the point to where I'm not producing any more oxygen. But if I have a graph like this and this says rate, then that means I'm still producing it and I'm producing it at a steady rate. I'm producing it here, producing it here, producing it. I'm still producing it. The only time that you are not producing oxygen, you're not producing your products, is when the rate is 0. So that drop off down to 0, then that tells me now there's no more oxygen being produced. There's no more toothpicks being snapped. But it's basically the same line telling you two entirely different things based on what variable they have on the y-axis. So be careful for that. Which brings me back to the graphs that you guys made. So a lot of people did graphs like this. It's supposed to be line of best fit. It's supposed to be showing rate. To me, when I look at this, because this is showing rate, that's telling me that they're getting faster and faster and faster and faster and faster. This tells me that when we were doing the toothpick ACE thing, that we were getting faster, breaking the toothpicks the entire time because the rate was increasing. Is that what we did? Does that sound right? We didn't get faster and faster and faster. I mean, after maybe the first or second trial when we figured out how to, do them a little bit more efficiently, there might have been a little wiggle room there. But there comes to a point where you could only snap toothpicks so fast. I mean, you can only do so much. So this telling me that shows, I think maybe that we're graphing something that, we're probably graphing the volume rather than graphing the rate. And then Jaden turned hers in, and she's like, oh, mine's probably wrong. And I probably did everything wrong. And I look at it, and I'm like, well, that's what I'm kind of expecting to see. Because you're not really changing the rate of reaction while we were doing that. The rate remained relatively the same. If it was a line of best fit, relatively the same. So when I do our very first one, and I can't remember whose data this is, it doesn't really matter, and I find the rate of each of those, these are the rates, 0.70, 0.6, 0.6, 0.63, 0.6. It's relatively the same. We have a little bit of a bump right here as we're getting started and figuring things out, and then it kind of evens out. You can only snap toothpicks so fast. That's it. That's all you can do. When we doubled the amount of enzymes that we have, we about doubled the amount of time, or the amount of product that we produce. We about doubled the rate here, but 1.6, 1.5, 0.88, that's about 1. And this was about when we ran out of toothpicks anyway, so it did affect our rate. It still really didn't change it. We were doing it twice as fast, but across, if we had unlimited amount of toothpicks, it would have been the same rate throughout the entire 3-minute time period. When we added inhibitors to it, we started out about the same, but then, you had a sock on your hand. It was hard to snap a toothpick. So it definitely slowed down, but it was consistent pretty much across there. We didn't really speed up or slow down or anything like that. We just had to figure out how to snap those toothpicks. So the inhibitors affected things, but they didn't affect the rate. They didn't change the rate. And that's relatively what you expect to see. At the very beginning, you're probably going to have that exponential change because you just added the enzyme in there or you just added the substrate. And so it's foaming really, really fantastically. But eventually it gets to the point where an enzyme can only do its work so fast. So what's the ideal conditions for that enzyme to do its work? Does that stuff make sense? Kind of, sort of. Okay, we're going to look at more graphs next week. But that's my tip to you because you're here, and we'll see if anybody watches the video, is make sure you're paying attention to the variables on the x and y axis. It makes a difference as to how you're looking at it and interpreting it. All right. So you guys have about 20 minutes left. Swing back around. Finish up analyzing the spirometry graph. Keep in mind what we've got going on. Your course file is due next Thursday. That rubric is on Canvas, so you can go through that and see if you've got everything that you need. The AP Bio Unit 5 test, that is next Friday. Cellular respiration, enzymes, biodiversity. So make sure you want this to be a good last unit test, so make sure you have everything ready for that. And there was vocab way back at the beginning. I think vocab 9 or vocab 10 went with that as well. So make sure you have that stuff. You can use those notes on the test, so have notes so that you can use. And then the following week is the Unit 3 test for HBS. As far as the stuff from Monday, Tuesday, and Wednesday, I'll update. Most everybody's got almost all of that stuff done. I'll look at the lactase thing, the simulation later on. I'm not worried about that right now. But for sure, the unit, the Kahoot over Unit 3 and 4, I think, for AP Biology, that's a good one because it involves enzymes and cellular respiration. The Mastering Biology, Chapter 6, definitely good. Extra credit, Chapter 7 for Mastering Biology. I highly recommend that as well. College Board videos, that's Unit 3. That had to do with cellular respiration and or enzymes. I can't even remember what it was, but definitely good stuff. So if you haven't done that, you can always go back and do those things again. That will help you out at least for next week, and then you can focus on the HBS stuff. Okie doke. And remember, HBS review, there's information about that up there and on Canvas. All righty.